Hello everybody, thank you very much for coming to my presentation. I'm Rafa Galvez. I'm a PhD student in COSIC, Karl Leuven, and I will be presenting joint work with Vilasa Munsami from Ruhr University of Bochum and Claudia Diaz, my advisor here in Leuven. The paper is called Less is More, a privacy respecting Android malware classifier using federated learning. Let me introduce you briefly to the problem. In traditional federated learning, the goal is to train a shared model that keeps the data local to the users but still learns from the federation of all of them. How does it do that? Well, first, users train a local model in their own device using their local data. And instead of sharing the data, they share the parameters of the model with a cloud or service provider that will aggregate all parameters across users and produce what is called the federated model. This federated model, its parameters, will be shared back to clients so that they can benefit from the learning process of all the other clients. In traditional federated learning, we assume that users can provide with labeled data, ground truth, for the local process, training process. On the other hand, it has been shown that federated learning, as depicted in this picture, is vulnerable to privacy and integrity attacks. Our problem we try to tackle is twofold. First, we get rid of the assumption where users need to provide ground truth. This is important for applications such as malware detection, where users just cannot provide with ground truth, because the point of the classifier is to actually tell the user if the application is malicious or not. On the other hand, we also try to address the security and privacy problems by designing a system that is resistant against poisoning attacks and against membership inference attacks. How do we do that? Well, for the first part, where the users can provide labels, we make use of semi-supervised machine learning. For the second part of security and privacy, we address what we believe is at least one of the root causes of the problems in federated learning, which is the number of parameters that is typically shared by clients. So we reduce the number of parameters that are sent in each of the model updates. Let me explain briefly what semi-supervised machine learning. In supervised machine learning, without the semi, you have data points that are labeled. For each of these data points, we know if, for example, this app is malicious and this app is clean. And the machine learning model will draw a line, will infer a rule that distinguishes between both classes. This is only making use of data for which we have labels. Unfortunately, we not always have labels, as in the example of malware classification and locally trained models. But this is more applicable to other applications where just a lot of unlabeled data is just discarded because there are no labels. With some supervised machine learning, we make use of both labeled and unlabeled data to predict, to infer a rule that separates classes. One specific type of semi-supervised machine learning is called safe SSL. This safety does not come from security or privacy, it comes from performance safety. In the sense that the semi-supervised model, the safe SSL model, assures that the model itself will at least match the performance of some baseline classifier. In our paper, we will make use of one specific model called SafeW, where the semi-supervised model is just an ensemble of classifiers weighted with these alpha weights. And the assurance is that the predictions in F that are yielded from these alpha weights and the baseline and the base learners, each of these learners, at least match the performance of the baseline predictions. So how do we use SafeW to create LIM or less standing for less is more? Well, we essentially federate SafeW. We make each of the clients install a SafeW model and also the cloud as well. The cloud will train the models, and then each of the clients will just use their apps to predict the weights. Note that these weights, these alpha weights, are very few compared with traditional federated learning models. If a deep neural network typically has hundreds, if not thousands of weights, our client weights, the ensemble we have, is for example 5 weights. This will be very important later for the security analysis. How does a federation round work? Well, first of all, the cloud will train the baseline classifier and the base learners using possibly supervised models, or maybe semi-supervised as well. In our case, we only used fully supervised model. That is, we make use of the label data from the cloud. And we believe this assumption is reasonable for applications such as malware detection, where service providers actually have ground truth for at least a set of apps. Once they have trained these models, they will share them with each of the clients, and then clients will use the locally installed apps for which the cloud has no visibility over to estimate the alpha weights of the SafeW model. These weights will then be used to predict locally either as they are without any other input, or in subsequent rounds, not in round 1 but in further rounds, with the federated weights averaged with them. So that means that in step 6, the clients will share their weights with the cloud, and the cloud will do an aggregation with them. What kind of aggregation? Well, we design a pretty simple aggregation algorithm where the cloud first averages the client weights and then takes the average or the median, in this case it's the same, between the client and the cloud weights. Remember, we also have a SafeW model in the cloud. For this, to compute these cloud weights, the cloud will use its own unlabeled data. So these weights will be what we call the federated weights that will be sent back to all the clients. We don't need to necessarily to update the baseline classifier and the base learners, but we do need to send the federated weights back to all clients so that they can again average their own locally estimated weights with the federated weights. Notice that the design is pretty conservative. First of all, as I said before, there is a very low number of parameters in the model updates. Let me go back one slide. These client weights, the number of client weights is actually the same as the number of base learners that the cloud shares with the clients. This number of base learners doesn't need to be big. It's the quality of the base learners that matters, not the quantity. That means that we can have very few client weights. In our experiments, we actually have only 5 client weights. So we believe with that we will reduce a lot the space for poisoning attacks and integrity and privacy attacks. Furthermore, there is a strong influence of trusted data in the model federation. By virtue of averaging the already averaged client weights with the cloud weights, we are giving a lot of importance to the weights that are computed using only the unlabeled data from the cloud, and we assume this cloud data is safe from the integrity adversary, because the cloud has no interest in pursuing its own model, and we assume the infrastructure is secure against external adversaries for the data. So this was a very high-level overview of the paper. Now let me go into the evaluation, first with performance. First, we sampled the cleanups from the Android top 3 most popular stores. And then we sampled the malicious examples, the malicious apps from the Android genome and the Android malware dataset projects. We actually sampled 50,000 apps, 25K clean, 25K malicious. In the paper, we also report results with other dataset drawn from the mandatory paper. But in this presentation, I will stick to our own dataset results. So we implement LIM using Python, and we need to choose a set of base learners and a baseline classifier for this FW ensemble. In the FW paper, they actually choose pretty fancy models. In our case, we wanted to focus on checking if we can learn from the federation without ground truth in the clients, and also if we can withstand security and privacy attacks. So we didn't want to look for the best performance. We wanted to check those two things. For that reason, we just use very vanilla models, one KNN with n equals 3, one SVM, 3 random forests, and one logistic regression. And we make experiments with all of them as baseline and the rest as base learners. In the paper, again, you have a table with all the averages of all the experiments. We simulate a federation with 50 rounds and 200 clients, each with a set of 96 pre-installed apps I drew from one of my own phones. So these are the performance results. On the left-hand side, you can see the false positives, and the right-hand side, you have the F1 score. We use the F1 score because the dataset is unbalanced in the clients, at least. We make clients install apps from 0 to 5 per round, with probability 0.1 that they will install a malicious app. This is to reflect the fact that users are much more unlikely to install a malicious app than a clean app. On the other hand, we report the raw number of false positives, this is the raw number, in order to evaluate the feasibility of LIM being installed as a client application and not annoying the user too much. So one of the challenges of locally classifying malware, malicious app, is that false positives are very high, so you will tire the user if you keep warning it about applications that maybe they know they are not malware, or they just get tired of all the alerts. So we want to minimize the number of false positives. In these figures, we report results of one configuration where the baseline classifier is a KNN and the rest are the base learners. So in blue you have the baseline, the KNN. In red you have SafeW, that is the base learners without taking into account the federation. And then in yellow you have the LIM results, taking into account the federated weights. And you can see that at around round 24, 23, there is a big improvement of performance due to a drop from 5 to 3 false positives. And this gets reflected in the F1 score, where we jump from 0.4 to roughly 0.6. So again, we show that using the federated weights makes a difference with respect to SafeW. So we learned from the federation. Now we want to check if we can withstand security and privacy attacks. We will first check against an integrity adversary, a pretty strong adversary that owns 50% of the clients and wants to perform a targeted attack. The targeted attack aims to trick LIM into misclassifying a specific malicious app as clean. To do that, the adversary will leverage what we call the allied learners, that is, learners from the ensemble that already misclassify this malicious app as clean. The goal is to have an honest majority of these allied learners so that the ensemble itself will predict that this malicious app is clean. So again, the adversary is strategic, so it takes into account the architecture of LIM, and that means it has to gain this honest majority in 3 places. First of all, its own compromised clients, so these 50% of the clients need to submit poison weights where the allied learners have honest majority, with the goal of tricking the honest client weights into getting the same honest majority for the allied learners, and the same for the cloud. We formulate this attack as an optimization problem where the goal is to submit weights that are as close, as similar as possible to the honestly computed weights, making sure that these 3 constraints hold. So these are the results, and here you see the same graph as before, but with one more line in black. This black line is the one where report results from the poison clients, and we can see that indeed the poison clients do not track performance. It still improves over baseline, but it goes from roughly 2 to 3 false positives. LIM still outperforms FW, but it does a zigzag. So this zigzag means that every other round the adversary succeeds into poisoning a few of the clients. So by owning 100 clients out of 200, it will poison a few of them every other round. And this also gets reflected in the F1 score of the clients. Finally, to evaluate privacy, we adapt and implement the membership inference attack presented by Melis et al. In 2019 SMP. The goal is to identify which app users install in a specific round by isolating the contribution of a specific model update in that round. So it will isolate the contribution and try to see if that contribution matches what the adversary can train with one single app. So the vantage point is the service provider, and the data is the submitted client weights and the federated weights. What we see is that the attack just doesn't work. Why? Because there are too few weights, too few information. When the adversary trains the model using only one app, the weights are actually the same for all of the base learners. That's because there is not enough information to discriminate which of the base learners are better or worse for this testing data. That means that all of the clients, all of the weights will be equal. For example, in our case, there will be 0.2. And that just doesn't match any of the contributions of one single update. So as for future work, we would like to make experiments at scale, more than 200 clients and more than 50 rounds of federation, more applications where users just cannot provide with labels, and real-world data with an implementation that can be used by real users in their smartphones. So to conclude, we presented LIM that can do federated learning without user supervision. Clients benefit from more data and the federated weights, and we've shown it is resistant against integrity and privacy attacks. Thank you very much. If you have any question, I'm open to answer them. Thank you.